So in the last section, we defined the derivative of a function f at a point A, at a point x equals A, to be the limit as h goes to 0 of f of a plus h minus f of a all over h. And that expression tells us the instantaneous rate of change and is the slope of the tangent line at A. So f prime of A for every number A, since we can find f prime of A for every number A, we can view f prime of x as a function of x. Okay, so for this function, the x value on the graph is the input, and the slope of the tangent line at that point is the output. So think of it as like a table of values. Get x values, slope of the tangent line, and that defines a whole new function. So the limit definition of the derivative of a function f of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So it's the same as the definition at a point. It's just instead of using a specific number a to find a slope, we're using a variable x. So, I'm going to turn this on. I have a function graphed here, function f of x, and I want to sketch the graph of f prime of x, so the derivative function. And the basic idea when graphing a derivative function is to plot points in the form of x comma slope. So there's a few key points that we might start with. Places where the slope is easy to measure. Where might that be? Yeah, the maxes and mins, the vertexes. This point, and this point. The slope of the tangent line at those points is all 0. So f prime is going to be 0 at those x values. So it looks like -1, like a little bit bigger than 1 and a little bit bigger than 3. So -1, we have a 0 slope. A little after 1, we have a 0 slope. And a little after 3, we have a 0 slope. Okay, so we can plot the 0 slopes right away. And then we're going to look at what happens before and after and in between those 0 slopes. So let's look to the left of the first 0 slope and draw some little tangent lines and see what's happening to the slopes. So some tangent line, tangent line. So there's some tangent lines. What's happening as I move from left to right? What's happening to the slope of the tangent lines? It's negative. Yep, they're all negative. Yeah, it's deeply negative and approaching 0. Yeah. So y in my derivative function graph is representing the slope of the tangent line, very negative and approaching 0. So maybe something like that, right? Negative below the x-axis and approaching that 0 value. And then once we hit that 0 value, what happens to my slopes? They're positive. They're getting steeper and steeper until like right here, and then they start to head back towards 0. Right? So that's 0, they get steeper, 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 and then there's something happens here at about 0, and they get less steep, less steep, less steep, and head back towards 0. So they're at 0 here, then they're going to go positive, which means we're going to go through the x-axis up to the positive y values. And it's going to hit some maximum steepness and then come back down towards 0. So something like that. And I'm not trying to figure out exactly what the steepnesses are. I'm just trying to create sort of a qualitative graph of the derivative. Okay, so after this 0 tangent line, my slopes become negative again. And they get steeper until about here, right? Why isn't this working? There we go. And then they head back towards 0. So we're at 0, we go negative and we go steep, steeper, 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 steeper till about here, and then we get flattened back out. Okay, so we're going to be negative till we reach some maximum steepness, then we head back towards 0. And then after that 0, we go positive again, and they just get steeper and steeper and steeper forever. So my derivative function might look something like this. Exactly where the maximum point and this minimum point happen is hard to tell just using graphs, right? It could be higher, it could be lower. We'd have to try to actually measure the steepness of that line to plot it. But this is a good qualitative graph. So as you can see, when f of x is flat, what is f prime of x? 0. Yeah. Whenever we have flat tangent lines, that means f prime is 0. And if f of x is increasing, what can you say about f prime of x? Positive. All the places where f prime was increasing, we had positive slopes for the tangent lines. And if f of x is decreasing, f prime of x is negative. Okay, so the numbers in this next table that's on the next page, they represent the cumulative number of heartbeats a certain patient has t minutes after surgery. We want to estimate the slope of the tangent line at t equals 42 and give an interpretation of this number. What does that number mean for the patient? So I would like you to discuss that one in your groups for a minute or two, and then we'll go over it together. So it seems that there are going to be sort of 3 reasonable approaches to estimating the slope of the tangent line at 42. That's how they express that question, right? Estimate the slope of the tangent line at t equals 42. Okay. So we can't, right? Because we can't get the exact slope of the tangent line because we don't have, this isn't a smooth continuous function, right? So we'd have to estimate it by doing what? Taking an average rate of change. Yeah, so the slope of the tangent line at 42 is the instantaneous rate of change. So we can take an average rate of change on some small interval around 42. So we could use 40 to 42, 42 to 44, or 40 to 44. All would be sort of reasonable choices for the interval to use. So I could estimate the slope of the tangent line to be approximately, let's see, if I go, the interval around 42 would be 3080 minus 2806 over 4. Anybody do that calculation? 68.5. Okay. Or we could do 40 to 42, 2948 minus 2806 over 2. And what's that one come out to? Did anybody do that one? About 71. Okay. Or we could do 42 to 44, small interval after 42. And so I'd have 3080 minus 2948 over 2. And what's that come out to? 66. Okay. So let's think about what the units are on these numbers. So the numerator of what I calculated here, 3080 minus 2806, these are heartbeats, right? So these are beats, and 4 is minutes. So my numerator is beats and my denominator is minutes. So 68.5 is beats per minute. And the units are going to be the same on all of them. So we've got beats per minute. So that is giving us a heart rate for this patient. How many beats per minute on average? Those are pretty normal, right? I think. Anybody know? Yeah. Okay. Oh, I don't think I. Oh, I did. Okay. So the graph of some function y equals f of x is shown here. And again, your graph was a little messed up, but you have all the important pieces. On the same set of axes, we want to sketch f prime of x. Okay, so this is like the one we just did a little bit earlier. And I want you to try it on your own first, and then we will discuss. Okay, so if we draw a few key tangent lines, that might help us at a few different x values. So near 0, see, I'll do one here, and here. Near 0, what happens with the tangent line near 0? It's pretty steep. It's pretty big. So let's see, if I made a little table, it's big, right, at 0. Very steep. And then as I move away from 0, what's happening to the slopes of the tangent lines? They're decreasing. Yeah, they're getting less and less steep. So as x gets bigger, f prime of x is getting smaller. But is it going to get smaller forever and ever and ever? Like, is it going to go down towards negative infinity? No. What's it approaching? 0. So they're getting flatter and flatter and flatter. This graph doesn't look like it's ever turning around. We're just going to assume that it keeps doing what it's doing, right? So it looks like these are actually approaching 0. So when I draw my sketch of f prime, I need it to start really big. So when x is 0, I need it to like be really big. And then I need it to decrease towards 0, but never get to 0, right? Because these are going to keep getting flatter and flatter and flatter, but this function is always increasing, which means that my derivatives will always be positive. They'll never be 0. So I want to draw a function that starts big and approaches 0 but never gets there. So I have something that starts big and approaches 0 but never gets there. As I get closer to 0, it gets bigger and bigger and bigger. Does that make sense? It's going to be huge. Yeah, yeah. So I have that heading up towards infinity. Yep. All right. So that graph, you probably recognized it, is the square root of x, the original graph that I gave you. So what I'm going to do is I'm going to use the limit definition to find the formula for the derivative of the square root of x and see if it matches the picture I drew. So I want to find the derivative f prime of x for the function f of x equals square root x. So I'm going to write down the limit definition. The limit as h approaches 0 of f of x plus h minus f of x all over h. So then I'm going to plug some stuff in, right? F of x is the square root of x. So I'm going to put an x plus h into that function. And again, carry along your limit as h goes to 0 at every step. So this is the square root of x plus h minus f of x, which is the square root of x, all over h. Okay, so what happens when I try to plug in h equals 0? You get 0 over 0. Yeah. The numerator, when you plug in h equals 0, you get root x minus root x, which is 0. And the denominator is just an h. When you plug in a 0, you get 0. So I have 0 over 0, which means I have to do what? I have to simplify what's in those parentheses before I can try to take the limit. So any ideas? I mean, I'd really like to get an h to cancel. Square what? Square root everything? Square the numerator. To the 1/2? I could. I don't know. squaring seems like a good idea. If I square my numerator, you square the first and we get x plus h. You square the last and we're going to get plus x, right? When you square root x, square root x, you get x. And then you take the product of the two in the middle and you double it. So that's going to be 2 square root x plus h over h. Okay. So I'm doing this, right? That is square root x plus h minus square root x times, and then you gotta FOIL it out. So my firsts are gonna give me an x plus h. My outer and my inner is what caused that to, it's gonna be plus, right? Because it's, no, it's minus. Minus, I have root x plus h, and I have 2 of them. And then my last is a negative times a negative, which is a positive. Root x times root x is x. All right, so this is x plus h minus 2 times the square root of x squared plus xh. Because when you have radicals, you can multiply what's underneath. Plus x. I don't know, is this helping? Yeah. Yeah, we still have h's, we still have radicals, nothing has canceled. All right, so maybe this was not the best approach. Minus the square root of x over h, sure, yeah. That is definitely a possibility. Still can't plug in 0, though. You know what would have been nice? When we were doing this one, if we had done the outer and the inner and they canceled, that would have been fantastic. Yeah, so instead of squaring this guy, maybe if we had multiplied by square root x plus h plus square root x. Yeah, question?
Yeah, no, I'm just curious, like, would squaring be valid anyway? Because doesn't that mention?
Yeah, right. Yes.
Like squaring.
Right. Right. Yep. Because, yeah, you're right. We totally would have been changing the value of the thing we were working with. You can't just randomly square stuff and have it be equal to what it was. So I am going to multiply the top and the bottom of this fraction by the conjugate of the numerator. And that's valid because now I'm just multiplying by 1. Right? So I've got square root x plus h minus square root x over h. And I'm going to multiply by the conjugate of the numerator, square root x plus h plus square root x over square root x plus h plus square root x. So now when I do my FOILing on my numerator, my firsts give me an x plus h. My outer and my inner cancel. They're the same, but one's positive and one's negative. And then my lasts, I have a negative times a positive, which is a negative. Square root x times square root x is x. Over, yeah, h times square root x plus h plus square root x. My x's in the numerator cancel, and I'm left with just an h, which I could cancel with the h in the denominator, because that's just multiplication. So then my h cancels with that h. And I forgot to write limit as h goes to 0. So I'll just write it out one more time. Limit as h goes to 0 of 1 over square root of x plus h plus the square root of x. What happens to that function as h goes to 0? Yeah, the denominator becomes 2 square root x. When that h becomes 0, the first square root becomes plain old square root x, and then you have square root x plus square root x, which is 2 square roots of x. So now when I'm plugging in the h equals 0, I don't have to write limit anymore. And this is going to be 1 over 2 square root x. So let's look at that. Let's look at 1 over 2 square root x and compare it to the graph that we drew qualitatively. It will definitely approach 0. So 1 over 2 square root x. Just start with a standard window, zoom 6. It is approaching 0. That's probably not the best window to look at. Let's look at maybe -1 to 3, -1 to 10. Yeah, that definitely looks like the graph we drew. Qualitatively, it looks like it might get bigger faster and approach 0 faster than we drew it, but it's got the same shape and the same end behavior. All right, so we can use this now. We now have a formula for f prime of x for any x value. We don't have to do a limit every time we want to calculate an f prime of something, because we did it all in one step for a function. Okay, so if I want to evaluate f prime of 1, that would be 1 over 2 square root 1, which is a half. And f prime of 4, 1 over 2 square roots of 4, which is a quarter. And f prime of 9 will be 1 over 2 square roots of 9, which is 1/6. So this is a preview of something called the power rule that we're going to use to find derivatives of functions that look like x to the n. So if f of x equals x to the n, f prime of x is n x to the n minus 1. Okay, so you take the exponent, you put it in front, and you reduce the power by 1. So let's use the power rule to find the derivative of square root x, which we already found the long way, right, using the definition. So I would have to write f of x as x to the 1/2, right, to use the power rule. And that means that f prime of x would be 1/2 x to the what? -1/2. So I brought the exponent down in front, and then I have to reduce the exponent by 1, so I get -1/2. 1/2 x to the -1/2. Is that the same as 1 over 2 square roots of x? Yeah, it is. Negative exponent means put it down in the denominator, and 1/2 is a square root. So that is our little preview of the power rule, shortcut for how to find a derivative function. The x to the n. So if f of x looks like this, then the derivative looks like this. Yes. power functions. They have to look like x to the n. That's the only time you can use this particular rule. There are lots of other shortcut rules as well. So we've got a long way, right, using the limit definition, and a short way using the power rule. You can also have your calculator find the derivative of a function at a point. I'm going to run through this pretty quickly. Okay, so let's say I want to find the derivative of square root x at 1. We already know the answer is supposed to be a half because we've done this all out by hand already. I want the derivative of square root of x at 1. So in the math menu, option 8 is nderiv. So that's the derivative. So you choose option 8. And then the syntax for using nderiv is going to be function. And then you have to put x because you're just saying x is the variable. And then you put the value that you want to evaluate at. So I'm going to type square root x, comma, then x, just saying x is the independent variable, then comma 1. And when I press enter, this should tell me f prime of 1 is a half because we already calculated that. And it came really close because your calculator is not using derivative rules, it's using a numerical approximation to find the derivative. Kind of like it's doing like an average rate of change over a very small interval. Because calculators can't do limits. Okay, so use your calculator to confirm the answers to f prime of 4 and f prime of 9. So just take a minute, type in, you're just going to change this last number to a 4 and to a 9. Make sure you get the same thing. Yeah. Yes. So your calculator can also graph a derivative, okay, of a function. The only thing it can't do is find a formula for the derivative of a function. So you know that the function square root x, it can't tell you that the derivative is 1 over 2 square roots of x. It can evaluate the derivative at various points, and it can graph it if you want. So if we go to y equals, we're going to type square root x in y1. And then in y2, we're going to do nderiv again. So you do math 8. No. Okay, so let's see. So I want it to take nderiv of y1. So I do vars, y-vars, function y1. Then I do comma x, comma x. So I'm saying I'm telling it that x is the independent variable, and I want it to evaluate at every x. So then I close the parentheses. And one little handy trick is that I'm going to have it graph the derivative in bold. If you highlight that little diagonal line next to y2 and press enter, it turns to a bold line. So this way you can tell which graph is which. All right, so for window, that should be fine because I already know what the derivative function looks like. So I've got my square root x function and my derivative function. All right, so that looks like the qualitative graph that we drew, and it looks like the graph of 1 over 2 square roots of x. So these are really good ways to confirm. Once you found a formula, this can confirm your work. All right, so that finishes up the lecture.